Maybe I write the passcode here. Just a couple of minutes, we will finish digital signatures. And then those who want to leave can leave. No issue. Okay, jumping back to digital signatures. See, we are just going to make a small tweak to the formula. Here in RSA encryption decryption. To do encryption, we use the formula cipher text is equal to plain text power E mod n. Okay, for encryption we use ciphertext equal to plain text power E mod n, right? In digital signature, we take it as message power D mod n. The message here is the plain text. Okay, so instead of taking plain text power E mod n, we take plain text power D mod n. With digital signature, there is no encryption decryption. In digital signature, the intention is different. In cryptography, the intention is we want the message to be a secret. Okay, that's why we encrypt the message and send it to the other side. Okay, in digital signature, the message is not a secret. Okay, we want to authenticate the message like we do. Normally we say, hey, can you sign and put a stamp and give, put a chop and give, so that the document becomes authenticated. Same thing here. So the signature is meant for authenticating the document, but the document itself is not a secret. But the beauty of digital signature is, once you have digitally signed, I will show you my digital signature. Once you have digitally signed it, if you make any alterations, even you remove a full stop, it will tell you that after digitally signing, the document has been modified. I will show you that also. Okay, so that is the beauty of digital signature. So that is why here, instead of using the encryption key, the sender, the signer, actually uses the decryption key, his own private key to sign. Okay, let us take an example to understand this. Alice wishes to send an authenticated message m is equal to 5. So the plain text here is 5. Okay, to Bob using RSA algorithm, where Alice's public key n is equal to 33, encryption key is 3, private key d is equal to 7. So in digital signatures, everything is given, nothing is secret. Public key, private key, everything is given. Okay, nothing is secret. So derive the signature that would be used by Alice. Explain how Bob would verify that it is Alice's signature and not somebody else's signature. Okay, so AS means Alice's signature. A stands for Alice, S stands for signature. Alice's signature is equal to plain text, that is message power D mod n. In encryption, we use plain text power E mod n. So here we use plain text power D mod n. So what Alice does is, she uses her private key. She uses her private key to sign the document. Okay. So what is the plain text is 5. What is Alice's decryption key? Decryption key is 7. So 5 power 7. Now you see here, I say 5 power 7. 5 power 7. I stop using 5 length 7. Okay. Alright, now I come back. 5 power 7 mod 33. That is equal to 14. So 14 is the numerical value of the digital signature of Alice. Okay. So this is received by Bob. So Bob wants to know whether this signature is actually Alice's signature or somebody else's signature. So how to confirm this should be Alice's signature and nobody else. So the formula is slightly a small difference with the decryption. In decryption we use plain text is equal to ciphertext power E mod n, right? So ciphertext power D mod n. So here we use signature power E mod n. So what Bob will do is, Bob will take Alice's public key. Alice's public key is known to everyone. That's why we say public key, no secret. Okay. So Bob, BV stands for Bob verifies. So Alice's signature power E mod n. Alice's signature is 14. Encryption key is 3 and n is 33. So 14 power 3 mod 33 is equal to 5. Meaning you got back your original message. So when you get back your original message, it means it must be signed by Alice and nobody else. Can you tell me why? Why it should have been only Alice's signature and nobody else?
Because for Alice only.
The public-private key pair. The public-private key pair. That is, this E and D, they are a pair. E is 3 and D is 7. This is public-private key pair of Alice. That's why when Alice signs using a private key, it can be verified using Alice's public key. Why means, I forgot to tell you that here, I consciously told you E can take different values, right? Okay? Your D, the value of D depends on E. Because I want to be louder than your noise. And I have micro gets something. I'm not very sure. So if you want me to be here, you stop talking. So here, E can take many values. The value of D depends on the value of E. That's why I said earlier, when we say public-private key pair, they are mathematically related, mathematically connected. This is the connection. Okay? Your value of P depends on the value of E. So when E is 7, so E is 3 here, you are getting D as 7. When E is 7, you will get D as 3. When E is 19, your D will not be 7, D will be something else. When your E is 11, D will be something else. When your E is 13, D will be something else. That is why there is a dependency between the private key and public key, E and D. This is the mathematical relationship. Okay? So that is why I said the public-private key is a pair. So this private key or public key only will work with the other key. Okay? This public key will not work with another private key or another pair. No, it won't work. Okay? That's why in digital signature, Alice uses her private key to sign, and Bob verifies using Alice's public key. Okay? And this is covered in all cyber laws. Cyber laws means in any country cyber laws, including Malaysian cyber law. Okay? This will stand on code. Because after signing, Alice cannot say, no, it has been forged, it has been signed by somebody else. No. Your hand signature can be forged. You yourself can put a signature and you can dispute. This is not like signature, somebody forged it. It's very difficult to prove it or disprove it. But this will stand in court. Alice cannot dispute after signing it is not my signature, cannot. Because the public-private key is a pair. It won't work with any other key. Okay? So, to show you RSA, one real-time example. One example is your AP. Your access point uses RSA. Your wireless access point uses RSA. One practical example. One more practical example is digital signatures. I will show you. Okay, so this is my digital signature from Adobe. You can see here it says signed and all signatures are valid. Okay, document content is not a secret. You can see digitally signed by Dr. Raja, date. This is not an image. You see my cursor here, and when it comes on top of signature, you can see a hand symbol. You can see public key RSA 2048 bits. It does not use 1024 bits. So here, Adobe digital signature uses P as 2048 bits, Q as 2048 bits. It also uses RSA. And it uses SHA1 for exchanging the keys. See, private key, it is hidden. Okay. An example for digital signature. So if I go and do some changes, actually it's very difficult. You can't edit it. First of all, you can't edit. You want to edit, You see, this document has been signed and cannot be edited. Not edited. So meaning the content cannot be modified. I can modify. How I can modify means I have to go and clear the signature. I can do it. I can clear my signature, but others cannot go and even edit the document because it will say it has been locked, cannot be edited. Okay. So you can remove the signature only if you know my private key. I myself don't know what is my private key because it is issued by Adobe. So I also don't know. So I signed. I can edit it because it is my public private key plan that works. Okay. Yeah. That is the beauty with WhatsApp. Even WhatsApp company cannot decrypt your message. What you said, that's it. That's why they say it's end-to-end encrypted. Actually, there's a story behind why WhatsApp went for that end-to-end encryption. There was a litigation on WhatsApp. So they said we need to protect customers' privacy. So they said we cannot, share you the key to find out what is the original message. So they want to safeguard the customers. So they went for end-to-end encryption. Okay. So I don't want to go there because I know you have to reach 47 and thanks for tolerating me. I slipped by 10 minutes. So I will see you on Saturday. Those who wish to join, you can join. Thanks to you on Saturday. Otherwise, I'll see you anything. Have a good evening.